Okay, in this video we're going to cover chapter 18, the sea floor. So when we think about the ocean floor, what do we envision? Well, that really depends on how much pop culture you may or may not have seen. But generally speaking, how many people have actually seen the sea floor? That's very few. And why? Because it's covered by the oceans, obviously. So, how do we have any knowledge about the ocean floor? Where does our knowledge about the seafloor come from? Well, originally, our knowledge came from dropping weighted lines over the sides of ships and lowering them down to the point where they would hit the bottom, and then measuring that distance, measuring how much of that rope is underwater. In the 1920s, something called the echo sounder, later to be called sonar, was invented. And this is basically an instrument primarily for measuring depth. So it sends a sound wave out into the water and measures the time it takes for that sound wave to return. Knowing what the speed of sound is in the water allows you to then calculate the distance to an object to the bottom. From there, we developed multi-beam sonar, which employs an array of these sound devices and listening devices to be able to map out a width or a strip of the ocean floor. And we have moved into also using seismic reflection profiles, where low energy sound waves, either from explosives or from high tech speaker systems, is able to send out these very low frequency sounds that go into the ocean, reflect off the bottom, and come back to us, and then can be measured. Some of these actually are able to go down in through some of the sediments of the seafloor, so we can actually reveal contacts or fault zones within the seafloor itself and see a little more of the detail below the immediate surface. We also, in the last 15 or so years, have developed methodologies where we're able to use satellites and use radar altimeters to measure subtle differences in the surface of the sea floor. And the reason this works is that the way gravity influences water, there's going to be small variations in the surface caused by the gravitational pull of features on the sea floor. So if you have a large mountain, it's actually going to cause the sea floor, or the sea level just above it, to be a fractional distance higher. So you can actually map out these areas where water is pooling up over something or not pooling up away from something, and create a representation of the sea floor bottom based on that data. Now, topographically speaking, we have three major units that make up the ocean floor. And those are going to be the continental margins, the deep ocean basins, and the mid-oceanic ridges. We're going to start with the continental margins. The continental margins now come in one of two generalistic types, based on their relationship to the plate boundaries for plate tectonics. The first of these is a passive continental margin. This is a continental margin that is found, generally speaking, away from an active plate margin. So it's on a continent, but it's not near an active zone. So it's not near a subduction zone, or it's not near a transform boundary. Generally speaking, for the current world right now, most of these are found along the coastlines of the continents facing the Atlantic Ocean. Generally speaking, they do not experience much in the way of any volcanism. They do experience earthquakes from time to time, but they tend to be few and far between. Generally speaking, they seem to be more associated with earthquakes related to isostatic adjustments. If you remember from chapter 16, at the end of the video, we discussed isostasy as this idea of if we take the Earth and break it into columns, equidimensional columns in terms of the surface area, and take those down to an arbitrary depth somewhere within the mantle, we can assume that the amount of mass in each column is exactly the same. The only thing that then changes is the volume of the materials and their density. And so for areas like the continents where we have a huge mountain range, we have a thicker layer of less dense material, which allows the mountain to be higher, where the oceans have a thinner layer of more dense material that still remains basically the same amount of material in each column. So, what are the features of a passive continental margin? Well, generally speaking, there are three parts of the margin we're going to go through. There's the Continental Shelf, the Continental Slope, and the Continental Rise. This is going from the continent towards the ocean. So, what's the Continental Shelf? Well, the Continental Shelf can be thought of as the portion of the continent that is flooded by the oceans, which means that the Continental Shelf is very variable. It's dependent not only on what's happening with the continental margin in terms of its isostatic adjustments, but it's also dependent on things like sea level based on what's happening with the world climate. So if you imagine 18,000 years ago during the height of the last ice age, where sea level could have been as much as 200 feet lower than it is today, then the continental margins, especially the coastlines, would have been further out to sea than they are today. This is an interesting idea in terms of archaeological ideas, because back then it's very much possible that humans would have been living along coastlines because of the nature of the ocean in terms of benefit for food and travel. So it could be that there is a lot of the human story in terms of our migrations, in terms of our cultures, that is currently buried under the sea and needs to be explored. So this is an area that is developing in terms of archaeology. Generally speaking, as I've tried to draw it out here, the continental shelf tends to be gently sloping. There are some areas where it is so gently sloping you can walk out quite a ways from the coastline and still not really get too deep into the water. Also, generally speaking, it tends to contain important mineral deposits. The most common ones that people will think of for this is going to be petroleum and natural gas, but also sand and gravel. Some of that can be coming from river deposits or from glacial deposits. And then also in the river deposits and some glacial deposits, there's now been a movement for finding gold in the continental slope or continental shelf areas. So there's a lot of different materials that we can gather from this. And generally speaking, there tends to be a fairly thick layer of shallow water sediments on the continental shelves when they've been buried under the ocean. Specifically, we tend to see, if we start from the coastline outwards, we see sand verging into muds, verging into limey muds, which would give us a sedimentary rock sequence of sandstone, shale, limestone, which is a very common sequence to see actually in the world multiple times over. If you take historical geology, we'd actually talk about this sequence and what it means when we see it on the earth, and how we can interpret what happens with sea level from it. Now, generally speaking, the next structure out in terms of the continental margin, a passive continental margin, is the Continental Slope. The Continental Slope is basically the area of steep slope coming off of the continental shelf going down towards the deep ocean basin. It's basically the seaward edge of the continental shelf. It's very steep, and it's kind of close to being the actual boundary between the continental crust and the oceanic crust. Okay. One of the things that we will see off of this sometimes is canyons. Some of these may have been cut by riverine courses when the sea level may have been much, much lower. but some of it is also just structures that are caused by erosion as material occasionally comes off of the continental shelf and goes down the slope and causes a abrasional erosion under the water, basically underwater landslides. Beyond the continental slope is the Continental Rise. This is the transition between the deep ocean basin and the continental slope. So this is the transition zone between the ocean sediment and the ocean crust and the continental crust. Generally speaking, we only find this where subduction zones are absent. So this is one of the primary differences between a passive margin and an active margin. In an active margin, we don't tend to see the continental rise. In a passive margin, we do see it. Generally speaking, the slope merges into a more gradual incline, which is what the continental rise is. We do see a thick accumulation of sediments on the continental rise. Sometimes we see very specific sediment deposits on there, deposits that have graded bedding, so that the bottom of the layer, as you recall, would have a thicker or larger grain size, and the top of the layer has a much finer or smaller grain size, indicating in this case, because it's underwater deposits, it was found from what we call a turbidity current, or an underwater landslide, basically. And sometimes these form underwater alluvial fans or sea fans. Now, in terms of active continental margins, basically the continental slope descends abruptly into a trench instead. These tend to be found mostly along the Pacific coast. You also can see a thick wedge of sediment at the edge of the continental slope that is called the accretionary wedge. This is material that is literally being scraped off the subducting slab. So if this hand here is going to represent our overriding continent, and this arm is going to represent the subducting continent, now imagine it's like a razor blade. This is like a razor blade. If you've ever shaved any part of your body, doesn't matter, and had some sort of imperfection on your skin, be it an ingrown hair, a pimple, a mole, whatever, you run the razor over it. Occasionally, what happens, the razor scrapes the top of it off or cuts the top of it off. This is what's happening with the accretionary wedge. The accretionary wedge is like a giant razor blade, and it's scraping material off of the subducting plate. And this gets added onto the edge of the continent. We'll talk about this more in a while. But basically, this is a way of adding material on to the continent. So, how about the deep ocean basin? What are some features of the deep ocean basin? Well, the trenches are a feature that we've already talked about. Again, they're long, they're narrow features. They tend to be the deepest parts of the ocean. The Marianas Trench is so deep that if I had a magic cookie cutter and I could pluck Mount Everest off of the earth all the way down to sea level, take it from sea level to its peak, turn it upside down, and put it into the Marianas Trench, point first, the bottom of the mountain that I cut off at sea level would still be more than 1,000 feet below sea level. So the trenches are deeper than Everest is high. Again, most of the trenches tend to be located along the Pacific Ocean at this point in time. There are a few in other locations. Namely, there's one along the coast, or not the coast, along the Caribbean islands in the Atlantic. There's a number of them in the Indian Ocean. So they're in different locations around the world. But most of them are the Pacific Ocean, the Pacific Ring of Fire. And this is, again, the site where the underlying oceanic material making up the subducting plate is being subducted back into the earth where it's being recycled. And of course, with that, we have associated volcanic and earthquake activity. The second feature of the deep ocean basin are the abyssal plains. These are probably some of the flattest places on the earth, and they're this way because they are just simply accumulating very thick blankets of what is called ocean snow, deep ocean snow or pelagic snow. And all that is really just sediment, fine-grained sediment, whether it is the remains of dead animals or plants, dust, etc., just raining down and leveling out the bottom of the ocean at that point. The abyssal plain is found in every ocean. It's there in every ocean, no matter what. Then we also have what are called seamounts, goyets, and oceanic plateaus. Basically, these are volcanic features that are found on the ocean floor. And I'm going to draw this out for you. I want to use Hawaii as an illustration for this, because Hawaii is actually a really good illustration of this. I'm going to draw this out a little bit exaggerated to try to make the point a little clearer. So, what I'm drawing is a cross-section through the ocean floor for Hawaii. It's going to be exaggerated vertically and horizontally in different ways. And I'm going to kind of make this a little more, a little less complex than reality, just to also get the point across. So, a seamount is going to be a underwater volcano that has not breached the surface. So if you were to go to Hawaii, off the southeast coast of Hawaii is a new island that's forming. It's about 10,000 feet below sea level still, so almost 2 miles, called Luihi. Strangely enough, true story, you can actually look it up. There are people who are selling plots of land on the new island before the island has ever appeared. It's probably about 10,000 or so years before this island breaches the surface for the first time, probably somewhere between 20 and 30,000 before it will stay above the surface for a significant period of time. But it would be like this. It's a little volcano underwater. That's a sea mount. Okay. Volcanic islands are a volcano that has breached the surface and is now above. This would be like the Big Island of Hawaii and many of the other islands of Hawaii, where it's at. This one I'm showing is active, so that would be the Big Island. It's the only volcanically active island right now that's above water. So this would be a volcanic island. So we have a seamount, a volcanic island that is now extinct and eroding away. Now, one of the things that will happen at this point in time is we'll also see reefs develop on these. So it's not uncommon on not only the active volcano, but on the inactive one to have reef structures develop on them. These are going to play a role later in it. Now, as the volcano weathers back down, it will eventually go back below sea level. Okay, nature abhors anything above sea level, so over time, all volcanic islands get weathered down. Once it goes back below sea level, that is what we call a goyet. Okay, so a goyet is a relatively flat-topped seamount that has been weathered down into a flat surface. It can be ringed with with re- coral reefs, and that can actually create atolls, which are circular islands that are sitting on top of goyets that are made up of basically reef material. But they will sink back down. Now, these structures tend to be large. Mauna Loa, the big island of Hawaii, is actually the largest mountain on the earth. Not the tallest, but it's the largest. But most of it is below sea level, so we don't really see it, we don't really appreciate it. Then we can also have vast outpourings of lava that cover large areas, but never really get to a high vertical extent above the sea floor, and those are going to be oceanic plateaus, very much akin to the idea of flood basalts on the surface of the earth. And that brings us to the third structure of the ocean, which is the oceanic ridges. The oceanic ridges, if you recall from chapter 1, are actually very important structures because they represent the spreading boundary between plates. So, generally speaking, what is an oceanic ridge? Well, an oceanic ridge is a broad linear swell along the divergent plate boundary where the plates are separating. So new oceanic crust is being generated in this area. They tend to occupy elevated positions. I'm going to draw this out for you in a moment. And this is because typically what we believe is happening is we have an upwelling of material from the mantle, and that is helping to push this area up. It's also less dense because it's hot, and therefore it's going to isostatically rise upwards. We tend to see a lot of faulting and earthquakes in these areas, although the earthquakes do not tend to be that strong. They tend to be fairly low-level earthquakes. We tend to see very high heat flow. We see structures based on that, such as the black smokers, which are basically underwater volcanic vents where very hot water, sometimes 700, 800 degrees centigrade, is coming out of the ground and carrying a lot of dissolved minerals with it that then deposit. We also tend to see a number of volcanic structures in the volcanic ridges. Basically, we're going to go through and look at this in a little more detail in a little bit, but they're basically very interesting features that, depending on how fast they're spreading, how fast is the material separating, is going to control some of the nature of the features that we see. Generally speaking, the mid-oceanic ridges or the oceanic ridges are actually the longest topographic feature on the Earth. They basically wrap around the Earth, covering over 70,000 kilometers or 43,000 miles in terms of their length. They make up about 20% of the Earth's surface by area, and every major ocean has it. Now, the term ridge is really misleading. If we were to draw it out in terms of a very narrow view, yeah, it could look like a ridge, but when we get into it, it tends to be much more complex. They can be very broad. Like this, with a deep central rift. This can be anywhere from 1,000 to 4,000 kilometers wide, which can give them more an appearance of a broad swell. These can have this deep faulted valley, a rift valley as we call it, that's bounded by a number of normal faults. It really depends on what's happening. Again, we're going to go through this in a little more detail here shortly. So, where does the oceanic lithosphere, the oceanic crust, come from? The concept formulated in the 1960s by a gentleman named Harry Hess. he kind of took the idea of Alfred Wegener, who was the father of plate tectonics. Alfred Wegener was a gentleman an Austrian, who studied a number of different sciences back in the early 1900s. He was a weatherman in an Arctic outpost, and at one point he noticed, as many people had before him, that there were certain weird things about the Earth that seemed to work out. One of this was, again, the idea that the continents would fit together, especially on the Atlantic Ocean. You could put them back together like puzzle pieces. There were rocks of similar nature and type across the ocean. There were fossils of the same type of species that cross oceans. So there were these ideas he had that the continents were moving, or continental drift as he called it. Generally speaking, his idea was not bad, but it never caught on in his time and wasn't accepted because he couldn't explain why the continents moved. Fast forward to the 1960s, Harry Hess starts noticing features in the ocean as they're mapping the ocean bottom that drive this idea that there's something happening with the ocean floor. Namely speaking, things that, like the thickness of sediment in the ocean thinned the closer you got to these oceanic ridges. The age of the rocks was very young at the ridges and got older the further away from the ridges you got. So the idea that Hess came up with is the idea of seafloor spreading, that the seafloor at this point is pulling apart and new seafloor is being made. This helps to explain why the rocks are younger at the ridge and older away from it, why the sediment layer gets thicker the further away you go for it, and it's almost non-existent at the ridge, as well as a few other features. So basically the idea is that the seafloor along these relatively narrow zones, called rift zones, is spreading apart, and as the plates move apart, new material is welling upwards into the fractures and generating new slivers of oceanic lithosphere, and it moves in a conveyor belt-like fashion. Combine this with the idea of continental drift, and you have the birth of plate tectonics. Now, generally speaking, the active area of rifting in a rift zone is only going to be between 20 and 30 kilometers wide, even though the ridge itself may be anywhere from 1,000 to 4,000 kilometers wide. So, again, why is this area elevated? Well, we believe it's mainly because the oceanic lithosphere is hot and occupies more volume than cooler rocks, as well as being more buoyant. As the basaltic crust travels away from the ridge, it's cooling and it sinks back down in relationship. And then also, the thickness actually increases due to the mechanisms that are produced in the mantle pushing it up. Now, the spreading rates and the ridge topography do appear to be interconnected. The ridge systems do indicate or exhibit topographic differences based on how fast the spreading is occurring within the system. So if we look at a slow spreading rate, i.e. the separation is occurring at between 1 and 5 centimeters a year, so basically around ½ inch to 2 inches a year total separation, what we see is that we tend to have a very prominent rift valley that usually has a very strong crestal ridge. It's usually between 30 to 50 kilometers across. It's usually very rugged, so it's got a lot of topographic distance in it vertically, which means in this case is going to be somewhere between 1,500 and 3,000 meters deep, which makes it very rugged. At intermediate spreading rates, which are going to be between 5 and 9 centimeters a year, what we see is that the rift valleys are more shallow, usually less than 200 meters deep. The topographic rate or topographic transition across it tends to be smoother. And when we get to spreading systems that are faster than 9 centimeters a year, we actually don't tend to see that much of a ridge, or I mean, not a ridge, a rift valley apparent. If we do, it's usually very narrow, only about 10 meters or 10 kilometers across, with a few topographic highs. And instead of being a rift valley, as I drew out earlier, it's more of a Horst and Graben type of feature where it's spreading but separating so fast that it's not separating as a single valley but multiple valleys. And again, this is just all due to the speed of it. But the faster it's spreading, the wider the ridge is going to be, because it's occupying a larger area while it's still hot, versus a slower spreading tends to be narrower. Now, if we were to drill into the ocean floor, what do we see? What does the layer of the ocean look like? What does this system create? Well, turns out it creates a very unique system of features that we can see. I have actually been to areas up near Strawberry, Arizona, where we can see this, because remember, as I said, in the subduction zone, it's like a giant razor blade that's scraping material off. Well, occasionally, if there's a big bump, that big bump gets completely sheared off and accreted onto the edge of the continent. We can see these in areas where these accretionary wedges have been made part of the continent. We see this in parts of Arizona, where chunks of the ocean floor were literally shaved off and made part of what is now considered to be the transition zone between the Colorado Plateau and the Basin and Range. So what are we talking about? Well, there's basically 4 distinct layers that make up the oceanic crust. Okay? Drawing it from the top down, the first set of layers, depending on where we're at in relationship to the ridge, is just sediment. Just sedimentary layers. Okay? Just the sediment that's settling down from the ocean. Below that, though, is a pile of what we call pillow basalts. The easiest way to think of pillow basalts is to think of toothpaste, but not normal toothpaste, really hot toothpaste that is being squeezed out underwater. And as it squeezes out, it solidifies, it hardens into rock. That's basically what's happening. The lava is oozing out underwater. It's solidifying into rock and forming structures that are very similar to those round. I'm going to draw it here. You know, you may have seen round pillows like this. Okay, in this case, they tend to have striations on the sides of them from when they squeezed out, and the surface tends to be rounded and broken. But we get these pillow basalts. They look like tubular pillows, basically. And so you have a stack of these tubular pillows. So when we drill into the ocean floor, the first layer we go through is the sediments. The next layer is the pillow basalts, and we can start to actually age date those pillow basalts. Now, the pillow basalts do tend to show a fair amount of hydrothermal contact type of metamorphism on their edges, so we actually have to sample these central portions of the pillows. Below the pillow basalts are what we call the sheet dikes. Okay, the sheet dikes are these vertical igneous structures. Basically, think of it this way, is that there's actually a dike of material that is coming up, and then this is where the volcanic event is occurring, that's creating the pillow basalts. Every once in a while, as this is pulling apart, a new central dike of liquid rock magma is created, and the edges of it are solidifying and moving away. So it creates this sheet-like structure of dikes within the ground. And then below that, okay, don't know what happened there. Camera stopped on its own for some reason, wasn't full of memory, but we'll pick it up from here. I'll try to merge these together in post, but we'll see what happens. If not, I'll just have to make a second video upload, which will be relatively short. So where I left off is we have the sheet dikes, and I was explaining how we have the central dike of liquid material, liquid magma, and it's pulling apart, and so the edges of that are solidifying, leaving a central dike, but just creating these new structures one after another after another. And then below this, we have basically a gabbro. Which is basically representative of the magma chamber that was making up the source of material for the sheet dikes and the pillow basalts. All of this together is what we call an ophiolite sequence, or an ophiolite complex. So this is something that we've seen by drilling into the sea floor. We have seen this sequence. We have also seen this, as I was saying, in rocks that have been scraped up in accretionary wedges on the Earth itself. There's some in Arizona. There's some in a number of different places. So basically, the basaltic magma is originating from the partial melting of mantle periddotites. The molten rock is injected into fractures above a magma chamber that creates the sheet dike complex. These are then making their way to the surface where they're erupting into lava flows that cool quickly and congeal, and it's forced to form these tube-like structures that we call pillow basalts. And then as this is moving away, the central magma chamber is also crystallizing and forming the gabbro. The seawater tends to circulate through this, especially the highly fractured crust and the pillow basalts, creating hydrothermal metamorphism, as I already mentioned, and that this is going to create, this is going to dissolve a lot of material from the surface regions of the rocks, dissolving ions and metals and forming precipitates as the water comes out of the structures and cool, creating the black smokers. Now, where does an ocean basin come from? Well, it comes from rifting. So the idea is what we call continental rifting. Imagine, if you will, a little over 200 million years ago, all the continents slammed together, forming Pangaea. And they sit like this for quite some time. And then at one point they begin to pull apart again. This is the rifting process, the continental rifting. So a new ocean basin forms when the continent begins to split apart into two or more smaller segments. There are some examples of this in the world active today. There's the East African Rift, there's the Baikal Rift, there's the Rhine Valley in Europe. The Rio Grande, actually, in North America is a rift valley. It's a failed rift valley, but it's one there. And then the Basin and Range of Arizona. Realistically speaking, based on my own personal observations, the Rio Grande Rift Valley and the Basin and Range are all part of the same rifting system. It's just that the Basin and Range represents the western side of that rift, and the Rio Grande Rift Valley, basically from the center of the Rift Valley to the east, represents the eastern side of it. This is partly due to the fact that when I was an undergraduate, I managed to go through an experience called SAGE, Summer of Applied Geophysical Experience. And it was held out of Santa Fe through a couple of different universities. one of the things that we learned at that time is that the amount of rifting or faulting that's occurred is easily accountable on the east side of the rift, but it's not accountable on the west side of the rift, and you actually have to go into the basin and range to start to account for those differences, those vertical differences. So it makes it a one-sided rift almost. Basically, today the Red Sea is an example of a rift valley that has lengthened and narrowed and created a linear seaway. If that spreading continues, the Red Sea will actually get wider and wider and wider, very similar to what the Atlantic did. The same thing with the East African Rift, except the East African Rift currently has volcanics at either end of it that is preventing the ocean water from entering the rift. Most of the rift is actually below sea level. So sooner or later, the ocean is going to find its way in there, and it will become a narrow sea like the Red Sea. Now, what is causing rifting to occur? There are a couple of different mechanisms that have been proposed. One is mantle plumes and hot spots, regions of hotter than normal mantle cause decompression or melting, resulting in a volcanic hot spot, and this is going to lift and stretch the continent. Could be that this just happens over time. If the continents don't move, they just heat up underneath, and that material then lifts and spreads. There's also the idea of slab pull and slab subduction, that the older oceanic lithosphere may be pulling on the continents that are attached to them and helping to pull them apart, or the force of the sinking slab basically causes this also. We're not going to get into this on the test, and just know that it happens. The old material, again, as it's subducted down in, it's going to sink in. It's going to approach a 90-degree angle as it bends down, and to be subducted, it tends to be destroyed by heating. Interestingly enough, the older the material that's being subducted, the steeper the angle it goes down. The younger the material, the shallower the angle. This gets to those the Wadham-Benioff zones that we talked about with earthquakes. We can see where the shallow, moderate, and deep earthquakes occurring. How far apart or how clustered together those are gives us an idea of how fast the subducting plate is being subducted. Let's see. Basically, one of the things that can happen is that the ocean basins can also close up. We know this has happened a couple of times when we formed the supercontinents like Pangaea or Gondwanaland in the past, or Rhodesia. We understand that there may be a cycle of opening and closings that we call the Wilson cycle. Exactly how that works is whether it's a yo-yo back and forth, or it's a yo-yo back and forth like this. We don't really know yet, but we hope to. We can only really reconstruct plate movements for about the last 200 million years based on the magnetic reversal stripes within the ocean floor, though we have evidence from other sources that gives us a way to reconstruct those movements beyond that. The Farallon Plate once occupied much of what's now the Eastern Pacific Ocean, but 180 million years ago it began subducting under the Americas, and it's been almost completely gobbled up to the point where now it's three plates, the Juan de Fuca, the Cocos, and the Nazca Plate. Most of the plate has been subducted and is continuing to be subducted. Beyond that, let's see, anything else I need to cover? No, I don't think so. So again, no clue why the video stopped short. Like I said, I'll try to see if I can figure out how to merge the two together, else they're going to be two separate uploads, and I'll make note of that. So I'll talk to you guys next time when we talk about plate tectonics and as a unifying theory, as well as convergent boundaries, the origins of mountains.